This is Donna Nelson, the University of Oklahoma. We're covering Chapter 2, Molecular Representations, out of David Klein's textbook. This filmed lecture matches, so it accompanies his textbook. The material presented here is covered in that chapter in the same order. So you should pull the chapter out and follow along as we go through this. That way you'll be able to see which points have been pulled out and are emphasized. This will help you separate the important material from the less important material. So let's go ahead. We're going to look a little bit more at certain characteristics of resonance structures and in particular lone pairs in those resonance structures. So we're going to draw more resonance structures via pattern recognition. Assess the relative importance of resonance structures, the resonance hybrid, and we're going to look at delocalized and localized lone pairs. So here we're going to group the material. So there's 5 general bonding patterns in which resonance occurs. Recognize these patterns. So you're going to have the allylic lone pair, the allylic carbocation. So that's a positive charge next to a carbon-carbon double bond. Lone pair of electrons adjacent to a carbocation. A pi bond between 2 atoms with different electronegativities. We've already seen some of these, but we haven't discussed them much. And then the conjugated pi bonds in a ring. The only way to recognize the patterns is to do many practice problems and examples, and there are lists of the problems in the textbook which have been assigned to you, and I selected those because those problems cover the most important points in the chapter. And so if you want to learn the important points from the chapter, work those problems. And so they are listed for you in a separate file. And you have the study guide that accompanies this textbook that is available to you. So you can work these problems and then look at the answers in the study guide. And that way you'll know if you're getting these correct or not. So vinyl refers to the actual atoms of the pi bond. This is about vinyl position. This is allylic. So these, the allylic positions, are next to the carbon-carbon double bond. So this is vinyl, and then move out one, this is an allylic position. Okay, so they can be in a cyclic compound or acyclic. They can be on carbon or on oxygen or on nitrogen. Here, this one depicts a lone pair on nitrogen adjacent to a pi bond. This is an allylic position. This one is not. It's not conjugated with anything. Okay, so this is not an allylic position. All the lone pairs drawn here are allylic. Do you see it's next to the pi bond? Next to the pi bond, next to the pi bond, next to a pi bond. 2 curved arrows are used to show the delocalization of an allylic lone pair. I will let you look at these so that you can see how 2 curved arrows are needed. One is needed to depict the movement of the lone pair. The other is needed to depict the movement of the pi bond. Lone pair, pi bond, lone pair, pi bond, lone pair, pi bond, lone pair, pi bond. So that will teach you here. Now we have a lone pair and a pi bond moving. So those show the 2 resonance structures. This is the allyl anion. Now we have lone pair, pi bond, and so this is an allyl anion. So here the negative charge is delocalized, Here, the negative charge is delocalized over carbon and nitrogen. Here, it's delocalized over carbon and carbon. If the allylic atom is neutral and it donates a pair of electrons, then it bears a positive charge. And the atom receiving the pi bond electrons becomes negatively charged. So here, the nitrogen lone pair is being donated. Nitrogen becomes positively charged. The pair of electrons in the pi bond between carbon and oxygen moves out onto oxygen. So this oxygen becomes negatively charged. Allylic carbocations. In allylic carbocations, you only have one pair of electrons involved. So only one curved arrow is needed because you're only moving one pair of electrons. If there are multiple double bonds, then an arrow will be needed for each pi bond. So here, this shows the pi bond being moved in. Now this arrow shows that pi bond being moved in. So the positive charge has moved to the other end of the molecule. 3 resonance structures are possible for this allylic carbocation. A lone pair adjacent to a carbocation, only one arrow is needed. So this pair of electrons moves in, the negative charge is removed from oxygen, and when this moves in, it satisfies the positive charge on carbon. Same thing down here. The formal charges are affected by the electron movement in these 2 examples, as you can see. So here, the pair of electrons on oxygen moves in, satisfies that positive charge, but when oxygen donates the lone pair, it bears a positive charge now. A pi bond between atoms of different electronegativity, as in the carbonyl. The oxygen is pulling a lot of density off of carbon, both through the pi bond and through the sigma bond. And so the pi system electron withdrawal is shown by this arrow. The pi electrons move out onto oxygen. Oxygen bears a negative charge. Carbon bears a positive charge. This is the extreme description of the carbonyl electron withdrawal onto oxygen. So this is totally covalent. This is totally ionic. The actual compound, as always, is sort of a mixture. It's a hybrid of these 2 structures. It's somewhere in between. Conjugated pi bonds in a ring. So each atom in the ring has an unhybridized p orbital. There's a p orbital here, one here, 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 here. And so each of these pi bonds can move one position, and when it does, you get a new resonance structure. So these are the 2 resonance structures. For benzene, you can see the arrow indicating resonance, and you can see the brackets indicating a resonance structure. The summary of the 5 main patterns is shown here. These are the ones that we went over. This involves 3 atoms. We just discussed this. The pair of electrons moves in, that pair of electrons moves down. Here, 1 arrow is needed. Here, 1 curved arrow is needed for these 2 atoms. 1 curved arrow is needed to depict the resonance structure for these 2 atoms. And here you have 3 curved arrows needed in this aromatic ring. So this is a summary of what we just covered. When we assess resonance structure, whether the resonance structure is a good resonance structure or a poor resonance structure, there are some things that can be examined. So not all will be equal resonance contributors. Some can, sometimes they can contribute equally, as in the allyl system, the allyl cation or allyl anion, where you have the 3 carbon atoms. But sometimes it's possible to draw a resonance structure that really doesn't contribute much at all, and it can just be totally ignored. So this shows, here we're going to discuss how to determine the most significant resonance forms. So those will be the major resonance forms, whether it will be a major resonance contributor or a minor resonance contributor. So the 4 rules, there are 4 rules. The three of them are covered here. The 4th one is in your textbook. You can read that one in your textbook. So here is the first one. So look to see how many filled octets there are around the atoms that are involved in the resonance. So here, carbon does not have the stability of a full octet. Here in this resonance contributor, carbon is surrounded by 8 electrons, and so is oxygen. So this is the major contributor. Now, the structure that has fewer formal charges. So here, this is a positive on nitrogen and a negative on nitrogen. Now, once again, you see the positive on carbon and the negative on nitrogen. So here you have charge separation. You want to minimize charge separation. There's no charge separation in this first resonance structure. And so this one is the largest contributor. This one is second because you have each atom is surrounded by 8 electrons. You have full octets, but here carbon is surrounded by only 6 electrons. So this is the largest contributor. This is a major contributor. If the compound has an overall formal charge, focus only on drawing resonance forms that show the delocalization of the charge. So here, you have a negative charge on oxygen, pull a pair of electrons in, form an oxygen-carbon bond, the pair of electrons moves out onto carbon, and so here you have a negative charge, there you have a negative charge. Over here, there's more charge separation. This is an insignificant resonance contributor, and it does not need to be considered. A structure with a negative charge on the more electronegative atom will be more significant. Here, oxygen is bearing the negative charge. Here, carbon is bearing the negative charge. And so this is the major contributor. Here, it's more stable for nitrogen to bear a positive charge than it is for oxygen to bear a negative charge, a positive charge, sorry, because oxygen is more electronegative. And so therefore, this resonance contributor is more important. Localized electrons are not in resonance. The localized electrons, in other words, the electrons involved in sigma bonds, are not involved in resonance. To be localized, the lone pair of electrons must be adjacent to an atom with an unhybridized p orbital. So the lone pair on nitrogen is delocalized because it is next to a carbon that has p orbitals, and the oxygen has p orbitals, so it's possible to donate that pair of electrons in, and this pair of electrons moves up. In one structure, nitrogen appears to be sp3 hybridized. In the other one, it appears to be sp2 hybridized because it's involved in a pi bond. However, remember that this resonance form, the actual structure that is represented by these 2 resonance contributors, can only have one structure. And so this requires that the nitrogen in that structure, the true structure represented by these 2 resonance contributors, the nitrogen in the structure must be sp2 hybridized. A lone pair is delocalized. It's only possible through overlapping p orbitals. So the nitrogen must be sp2 hybridized in the actual structure, even though it's not here in this resonance structure, or it appears not to be. The lone pair does not participate in resonance if it can't overlap with an adjacent p orbital. Okay, so notice here you have the pi system. On this nitrogen, that pair of electrons is orthogonal to the pi system. It is lying in the plane of the carbon skeleton. So it is perpendicular to the p orbitals. So there is no overlap at all. So this would not be a valid resonance structure. A lone pair is not delocalized just because it is next to a pi bond, therefore. So here we have a nitrogen atom that does have a lone pair on it, and that lone pair is delocalized across this system. As a matter of fact, that pair of electrons will be involved in resonance, and also it will create an aromatic ring. The pair of electrons on this nitrogen will lie in the plane of the molecule, the sigma skeleton, and therefore it will be orthogonal to the p orbitals. It will be perpendicular to the p orbitals. It will not be involved with the pi system. Therefore, it will be localized on nitrogen. This one, since it is not next to a pi system or a p orbital, it will also be localized. So this finalizes the discussion of resonance and of your everything that's needed to depict the resonance forms in the molecules, and as well as the molecular representations.